Hi, I'm Scott, and today we're going to look at how eBPF represents a new way of approaching chaos engineering by shifting some of its capabilities left in the development lifecycle. Chaos engineering was pioneered by Apple in the 80s, and I would say popularized more recently by Netflix's Simian Army. It lets us experiment on a running system in order to build confidence it will effectively tolerate failures. This means so far coarse-grained destruction of virtual machines and cutting networking off at different levels of granularity. We can do this sort of thing cloud style, so in AWS, as Netflix famously does. We can also do it using something like Chaos Mesh in Kubernetes, which in some cases is already using eBPF, which is cool to see. It lets us at a high level catch two classes of errors. One is the emergent behavior of all of the services, all of the components in my system is such that it fails in a poor fashion when we introduce this class of error. The other is this particular service, service 1, fails when we introduce this class of error, or rather fails in a way that isn't optimal. This stuff is great, especially for complex failures across multiple services. But on the other hand, it shouldn't really take an entire cloud environment to discover that service A is failing in a poor fashion when the network around it breaks, by way of example. The earlier we can catch these errors in the software development lifecycle, the easier and cheaper it's going to be to fix them because we're closer to the change that introduced them. Here as an industry, we've lent on component testing historically. It's somewhere in the middle of the testing pyramid, and the idea is that we spin up a service in isolation and stub remote service calls out. This also gives us a chance to introduce failures into those stubs and see what the thing does when those failures pop up. This is good practice, but tends to be quite cumbersome to code, particularly for failure cases, because we have to write a lot of stubs. If we have lots of downstream services, it's that many stubs, and then times the different number of failures we want to introduce, which means that we probably do this less than we could because of the friction involved in doing it. With eBPF, on the other hand, we have this universal language of destruction. We can go and inject the same sort of failures without having to extensively modify the code of the service under test, instead wrapping the whole thing up with some tooling that says, within the bounds of this call, break all network I/O that looks like X, this port, that sort of thing. This can be done generically with regards to the language of the service because we're doing it out of process with eBPF. And we also have the power to do it using the same tools regardless of failure mode, because eBPF lets us introduce failures in the network path and the kernel interface and the security module interface, all sorts of different things, but always with the eBPF tooling. So let's have a bit of a look concretely at how we can break things. Here we have a kprobe attached to the openat system call that's returning access denied for 50% of invocations made by targeted processes, where the targeted processes are passed in as a PID list in a map from user space. We use BPF override return to short circuit the system call and return an error back to user space, essentially making openat fail in a controlled way. This example is written concretely for openat, but because the system call interface is fairly regular in terms of how system calls are invoked and how error numbers are returned back to user space, we could also generify this up pretty well so that we have one set of probes that we use to fail all sorts of different system calls. In this example, we're using the traffic control subsystem and its filters to randomly drop traffic for targeted processes in the outgoing direction. First, we hook socket creation. If the socket's for a targeted process, we set a mark on the socket's skbuf, and we can then pick this mark up later on in the TC filter. We use tcact stolen to drop the traffic. This is a nice one for our purposes because it indicates to the caller that the traffic got through the packet pipeline successfully, so it looks the same as network packet loss happening outside of the machine. And we get that without having to pull cables out of switches and without having to have a full-blown cloud environment. So far this is really just a nice idea and a tech demo. I would love to see this sort of thing built into test frameworks with some common Golang eBPF backend and a bit of a UI bound into, say, JUnit, GoTest, what have you. It would be nice to extend it to use other potential probe points within the kernel. The express data path, for instance, seems like a natural fit for introducing coarse-grained network failures. And the LSM could be a good way of introducing security failures. It would also be nice to see other less absolute failure modes. This means resource exhaustion, for instance, potentially by tweaking cgroup limits. The experiments I've written so far and code from the slides is available on my GitHub. It's very incomplete, but you can run it and use it. Feedback and ideas encouraged. Thanks for listening, and enjoy the rest of the sessions.